Welcome back to the next video, everybody. Today we're going to cover the proof of Lemma 1 from the previous video. So let's get into it. So let's recall what Lemma 1 says. It says, let L be an odd prime, let A be a complete Noetherian local ring with residue field K of characteristic L, and let rho from GL to GL2 of A be a good representation. Then there is a map from H1 to GL mod ILA into H1F GLA, and this map is an isomorphism. And we're only ever going to really be applying this when A is O mod lambda to the n. Okay, let's get into the proof. So what we want to show is that the image of H1F GL add row inside of H1F GLA is exactly hom GL mod ILA, where we're considering continuous homomorphisms here. Go back to the chapter 4 playlist on Galois cohomology to see that this is why this is what we want to show. This is a little exercise. It's not even actually clear, by the way, that the image is in H1F GLA, so we have to show that too. We do know that hom GL mod ILA is the kernel of H1 GLA to H1 ILA. And I want you to check this, it actually suffices to prove that the image of H1F GL add row to H1 IL add row lives in H1 IL add 0 row. So this is another little quick exercise in definitions, essentially. From chapter 8, so this is the chapter on deformation theory, we know that H1F GL add row is isomorphic to DF row A bracket epsilon. So remember, A bracket epsilon here is kind of the ring of dual numbers over A. And this was kind of like a deformation space. Okay, so this is actually equivalent to the fact that if rho epsilon from GL to GL2 of A bracket epsilon is a flat deformation of rho, then we have a fixed determinant conditioned inertially. In other words, det rho epsilon equals det rho on I sub L. But rho and rho epsilon are both flat deformations of rho bar, so this is just true. Okay, so how do we prove this is true? It requires a partially hard theorem. Here's the missing theorem. So key theorem, we're going to let A be a complete Noetherian local ring with finite residue field K of odd prime characteristic L. We'll let rho bar from GL to GL2 of K be a good representation, and we'll choose a lift rho from GL to GL2 of A of rho bar. Okay, we know by the above that we just talked about, we know this admits an element of df rho bar of A. We'll let psi sub n denote the fundamental character of level n, and we'll let phi2 from IL to f star L squared, given by the map psi2, inject into GL2 of FL, inject into GL2 of K. So we'll look at this composition here. Okay, and then three things are true. So sorry, notability updated. I think it's atrocious now, but I'm going to have to kind of keep moving this a little bit more. So we're going to go up here. So first thing, if rho bar is reducible, there exist continuous unramified characters chi bar I from GL to K star, such that rho bar is isomorphic to omega. So this is the cyclotomic character, chi bar 1 star 0 chi bar 2. Otherwise, rho bar is actually absolutely irreducible, and rho bar is inertially at L isomorphic to phi2. Okay. So 2. If rho bar is reducible, there exist unique continuous unramified characters chi I from GL to A cross, such that we have kind of the same thing on the lift as we did above. So we have rho is isomorphic to epsilon, still the cyclotomic character, chi 1 star 0 chi 2. In particular, det rho is just epsilon on IL, and chi I mod the maximal ideal of A is nothing but chi I bar. So everything lifts nicely. Okay. And then 3, if rho bar is irreducible, then det rho is epsilon inertially at L. All right, let's get into the proof of this. I will leave it to you to see why proving this actually finishes the proof of Lemma 1. Okay, it's not too hard to see that. We're only going to prove 1 and 2 here. 3 is much harder, and we'll take care of it later. Okay, so for 1, rho bar is reducible. Well, let's suppose rho bar is reducible with diagonal characters, let's say eta 1, eta 2 from GL to K star. By local class field theory, on QL, we know that eta j is omega to the nj on IL. As characters for some integers, well, I guess for some classes of integers, nj and z mod p minus 1z. So this is just this is just class field theory for QL. Right? Now we know that eta 1, eta 2 is det rho bar, but that's also omega on IL. That's kind of given information and also definitions of these characters. So that means that eta 1, eta 2, the set consisting of those two things is the set consisting of 0 and 1 by a result of Raynaud from chapter 5. It's actually the last result in chapter 5, so I'd encourage you to go back and look at that. You can also see Theorem 1.7 on page 385 of Cornell, Silverman, Stevens for a more concretized description of Raynaud's theorem as it applies to this specific case. And so it remains to prove that if rho bar is isomorphic to eta 1 star 0 eta 2 with eta 1 unramified and eta 2 equals omega on IL, then rho bar splits into a sum of representations. Okay, that is, we have to show that rho bar has non-zero unramified quotient. Okay, so let's do that. Let's consider the connected Ital sequence, and you can go back and see chapter 5 for the basics of this, of the finite flat ZL group scheme G with generic fiber rho bar. Here it is. It goes from 0 to the connected component G0 to G to the Ital piece G at to 0. Okay. It is a standard fact that if L is odd, then a flat representation of GL is unramified if and only if the associated ZL group scheme is Ital over ZL. This is proven on page 390 and page 378, kind of in tandem of Cornell, Silverman, Stevens, but again, this is a well-known algebraic geometry thing. Using Raynaud's equivalence of categories, you can see the previous video, again, that was covered in chapter 5. And this fact, so this algebraic geometry fact, it's automatic that the generic fiber representation of G at is nothing but the maximal unramified quotient of rho bar as an FLGL module. On the other hand, if you recall that the connected Ital sequence is functorial, that was covered in chapter 5 as well, we find that the usual K action on G gives K actions on G0 and G at. Okay? So that is, the generic fiber representation of G at is also not only what it was above, it's the maximal unramified quotient of rho bar also as a K bracket GL module, not just as an FLGL module. Okay, so let's continue. This means that if rho bar is not split as a K bracket GL module, then G at is trivial. And so G is a connected group scheme by the connected Ital group, the exact sequence. However, we know that all sub-representations of rho bar are generic fiber representations of finite flat closed subgroup schemes of G. This is from chapter 5, and those are all connected as well. This means that such a representation must be ramified by that standard algebraic geometry fact that I mentioned above, but that's a contradiction to the existence of our unramified character eta 1. Okay, let's prove the second part of 1. So we're going to suppose this time that rho bar is irreducible. We've already seen, since P is odd and that rho bar is cyclotomic inertially in L, that rho bar is absolutely irreducible. This was an argument I believe we first introduced back in chapter 7. Okay. Since IL is a normal subgroup of GL, rho bar restricted to IL is semi-simple. This is really just a check with definitions. It's also tame. You can see Sarah Local Fields chapter 9, lemma 2 for that. Hence, rho bar restricted to IL is abelian. So rho bar restricted to IL, tensored up to F bar L over K, is isomorphic to chi1 plus chi2 for some continuous characters chi I from IL to F bar star sub L. All right? These characters have to take values in a quadratic extension of K, and they can't be equal since rho bar is irreducible, hence not abelian. So absolute irreducibility then gives us that Frobenius et al. Swaps the inertial lines. That's the only possibility. We're not working two-dimensionally here. Since conjugation of Frobenius on tame inertia is given by L power, this is kind of a standard number theory fact, we find that we have no choice but for chi2 to be chi1 to the L and chi1 to be chi2 to the L. And so chi1 is a character from IL to F star P squared, and chi1 of I sub L does not live in F star sub L. It's kind of a summary of the above. Okay, so let's continue. Since rho bar is flat, Raynaud's equivalence of categories says that his other result on fundamental characters, that is the last result from chapter 5, his other result, remember we proved 2 major results from him, actually applies to chi1. Well, that means chi1 is either psi2 or psi2 to the L. Psi2 is our fundamental character, okay? Second fundamental character. This just means that the semi-simple K bracket I sub L modules, rho bar sub I sub L, and phi2 are K bar isomorphic. This is really just definitions. But then by Brouwer and Nesbitt, they're actually isomorphic. Okay, and that's what we wanted to prove. All right, let's look at the proof of 2. We're going to reduce to the case where A is Artinian, hence finite. I would check both assertions. I would check that you understand that we can reduce to that case, and check that reducing to that case gives us actually the case where A is finite. Okay, then rho is the generic fiber of G. Since L is odd, we can use Raynaud's equivalence of categories again to say that A acts on G. We'll write down the connected Ital sequence of G. Again, I'm not going to do that. That just gives you the same sequence as above. By the universal properties of the sequence, A has to act on G0 and G at similarly to the above. And so taking generic fibers gives a short exact sequence of A bracket GL modules with rho in the middle. What we have to show is that G0 and G at have A modules associated to their generic fibers that are free of rank 1, and that the characters on these lines are of the type predicted by part 2 of the theorem we're proving right now. Okay, so let's do that. We first claim that all the ZL-GL module Jordan-Holder factors of the generic fiber representation of G0 are ramified. To see that, just notice that such representations are still flat, and any corresponding ZL group scheme is part of a decomposition series for G0. Recall that connectedness of ZL group schemes can be checked on the closed fiber, and that base change commutes with taking short exact sequences of finite flat group schemes. This is a chapter 5 thing. This immediately gives us that all closed subgroup schemes and quotients of connected finite flat ZL group schemes in the category of such group schemes are connected. A non-trivial connected finite flat ZL group scheme is not a tau. So by that standard algebraic geometry fact from earlier, its generic fiber representation has to be ramified, which is the claim. Okay, or which gives the claim, I guess. So let's let M at rho be the non-zero maximal unramified abelian group quotient of M rho. All right, we know this is the generic fiber representation of G et. So it has an A module structure. We talked about that above. By what we know about rho bar already, so from part 1, M rho bar equals M rho mod M sub A maps to M at rho mod M sub A. That map is surjective, and the latter guy is non-zero. Well, that means it has to be one-dimensional over K. Since M at rho can be generated by a single element, well, not since, I'm sorry. Hence, M at rho can be generated by a single element as an A module. Okay. We have to show this is free of rank 1, though. So to do that, we really only have to check that it has the same A length as A, which we're going to check shortly, but let's move on first. If we move on, the kernel M0 rho of the map from N rho to M at rho, that surjective map, that has to be the generic fiber representation of G0. So all of its Jordan-Holder factors are ramified by the first claim we just got done talking about. Okay. Actually, that claim gives us as that we're kind of ramified. The Jordan-Holder factors are ramified as A bracket GL or ZL bracket GL modules, and we need them to be ramified inertially, so we need to replace I here by I sub L. But you can just kind of run through the same argument and get ramification if we work over IL instead. Okay. So since the A and GL actions on M rho commute, the shape of rho bar that we already know about tells us that all A bar IL module Jordan-Holder factors of M rho are one-dimensional K vector spaces of the form K take twist, first take twist of K, or K. Since L is odd, K is certainly not isomorphic to K1 as GL modules. You can check that. I mean, there's nothing really to check, but all A bracket I sub L module Jordan-Holder factors of M at rho are just K, and those of M0 rho are just K1. Since M rho is free of rank 2 as an A module, and because its quotient M at rho has a single generator as an A module, as we discovered earlier, the number of unramified Jordan-Holder factors is at most the number of ramified ones. Okay. So now it suffices to show that M0 rho mod MA is one-dimensional over K. This is the second kind of piece here. Indeed, this would give us that M0 rho and M at rho are each quotients of A as A modules, and because M rho is free of rank 2 over A, they have to be free of rank 1 over A. There's no other choice. We don't have much room. Okay. Let's let rho prime be Ham A rho A1. You can inject A1 into a finite product of copies of QL mod ZL1 to give an injection of rho prime into a finite product of copies of the flat Cartier dual Ham ZL rho QL mod ZL1. So this was all these Cartier duals and this kind of thing. These were discussed back in chapter 5. Okay. So the upshot is that rho prime is a flat representation by Raynaud's equivalence of categories. Okay. I mean, you probably could have just suspected that, but there you go. So looking at Jordan-Holder factors then gives us that rho prime mod MA is reducible with cyclotomic inertial determinant. That allows me to apply part 1, which lets me conclude that M0 rho equals Ham A V at rho prime A1. Okay, which means that the inertial actions on M at rho and M0 rho are trivial and cyclotomic respectively, which proves what we wanted. And then the little kind of rest of 2 part, there's like a second little claim at the end of 2 there, that's just clear. Okay. All right. I think this should be an M here, actually. Sorry about that. We now showed that it suffices to prove that M0 rho mod MA is one-dimensional over K. So now let's actually prove that. Okay, and to this end, we just have to check that the right exact sequence 0 to M0 rho mod MA to M rho mod MA to M at rho mod MA to 0 is exact. Let's choose a finite set of generators. X equals the set consisting of all the xi's for MA, and we'll consider the natural AGL linear map from the direct sum over rho, one copy per x and x to rho, the obvious map, with co-kernel rho mod MA. Extend this to a diagram using the connected Ital sequences of each side and apply the snake lemma in the abelian category of flat GL representations. You'll get a co-boundary map there, and it must be 0 because any map between a connected and an Ital finite flat group scheme over a local ring is trivial. That gives me the injectivity of the second arrow, which is all I really needed because this was already surjective. Okay. So we're done. That actually proves that this is an exact sequence, which shows me that this is one-dimensional over K. We proved here that showing that one-dimensionality proves the rest of 2. And so we are done. So we're going to go on. We're going to look at the proof of lemma 2 from the previous video next time, and I'll see you then, and thanks for watching.